Hello, my name is Jenna Nichols. Today we're going to talk about IB Chemistry Structure 1.3.4, which gets into atomic orbitals, so S, P, D, and F, sublevels of higher energy levels. So let's just take a quick second to talk about the development of the atomic model. Really, the first scientist involved was John Dalton, who came up with the atomic theory that atoms are small, indivisible spheres that make up everything. And so this would be the Dalton atomic model. It's just spheres that can't be broken down any smaller. Now, since then, we've discovered other aspects of the atom, and we know that that's not quite true. So later on, with the discovery of the electron, this came up, J.J. Thomson developed what's called the plum pudding model, where it was this like positive stuff that the small electrons are embedded in. And then as we get into the next model, with the discovery of the nucleus, that was Rutherford's gold foil experiment. So he literally took a piece of gold foil and he shot alpha particles at the gold foil. And he noticed that almost all of them went straight through because the atom is mostly empty space. But every so often, one of the alpha particles would bounce back. And that's how he figured out there was a small, dense, positively charged nucleus, and the electrons are around the outside. Then with atomic emission spectrum, Bohr was able to develop the Bohr model, where the electrons travel in discrete energy levels, and they can't have intermediate energies. And then now we know it's something called the quantum mechanical model, where the electrons have a particular area of the atom that they're most likely to be in. We call those areas orbitals, and they make up the electron cloud of an atom. So Bohr, the Bohr model assumed that there are fixed orbits around a central nucleus, so like literally planets going around the sun. So he got the discrete amounts of energy right. However, the fixed orbitals, fixed orbits was not correct. The quantum mechanical model now kind of defines it as like a specific three-dimensional shape, and the electron is free to move around that shape with more likelihood in certain areas than others. So it's like a probability map when we're actually modeling the atom, but the electron's free to move randomly throughout the whole space. And it might not be spherical. It could have other shapes that the electrons are likely to move throughout, depending on the position and the distance from the nucleus. So that is the biggest difference. Bohr has these discrete orbits, and the quantum mechanical model has the cloud where it's able to move. So through some very complicated math, they're able to map the probability of finding electrons in different orbitals for the different energy levels of an atom. And we wound up with some of these different shapes. So the shapes we call S, P, D, and F, and that shape defines the specific orbital where the electron is likely to be found. S shapes are spherical. P are these dumbbell shapes. Now you should know that there are 3 p orbitals in each sublevel, whereas there's only 1 s orbital in each sublevel. You should also know that since this sphere is perfectly symmetrical, there's not really a different orientation, but with P being the dumbbell, there are 3 orientations. There's a X, Y, and Z. They're relative, of course, but you'll have those 3 orbitals at any given sublevel. D becomes even stranger. They have these like flower shapes, and this one, which I call a dumbbell donut. I don't know that anybody else calls it a dumbbell donut, but it's just a strange shape. You don't need to know the specific shapes here or the specific orientations, just that it is more involved than the p orbitals, and that there are 5 different orbitals in each sublevel. And then finally F, same idea. There are these even more complicated shapes. You just need to know that there are 7 per sublevel for a particular energy level that has F orbitals. So if we think back to the Bohr model, Bohr said that the electrons in a given energy level, there are 2 n squared electrons. So in the first energy level, there are 2 electrons. Those 2 electrons are going to travel in an s orbital. And we use boxes instead of drawing the funky shapes. We use boxes to represent those orbitals. In the second energy level, that can have 8 electrons. The first 2 can fit in an s orbital, but s can only hold 2 electrons. So then we can start using our p orbitals. Remember, there are 3 p orbitals in a sublevel, so we usually draw those boxes connected to show that those are the 3, like the x, y, and z orientations of those p orbitals. Then we have, in the third energy level, there can be 18 electrons. So 2 can fit in S. And then we've got our P, X, Y, Z. So we can get up to 8. And then you can get into the D. Now, D sublevels have 10 possible electrons because there are 5 orbitals. So 5 orbitals, different orientations. So if it's not already really, really clear, 2 electrons can fit in each orbital, and we use arrows. We'll get into this a little bit more in the next section, but just for now, we use the arrows to indicate the number. So you see that adds up to 8 electrons total. In our third energy level, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 electrons. So Bohr wasn't necessarily wrong, he just didn't have enough information. He wasn't specific enough with how the electrons are arranged in these individual sublevels in an energy level. And I also want to make it really clear, like this whole thing is the third energy level. Looking at S by itself, P by itself, or D by itself, those are sublevels. And each box is an orbital. So make sure you know the difference between those. So how do these different energy levels fit together in an atom? So the first energy level only has an s orbital. So we're going to start with our nucleus. You're going to have a sphere. You have to imagine this in 3D. A sphere that represents that s orbital in the first energy level. First energy level can only have 2 electrons. Second energy level is a little higher energy, so it's a little further away from the nucleus. And we're going to start with S as well. So that's second energy level, S orbital is a slightly larger sphere. Second energy level can have 8 total electrons. So we don't just have an S, we also have p orbitals. And we have our p orbital that's in the z orientation, in our x orientation, and in our y orientation. And so this is our 2p sublevel with 3 of those orbitals. Third energy level, we're also going to have S, so that's our 3s, even larger sphere. We will have 3p. I'm going to try to draw this. 1, 2, 3. We have our x, y, and z, and our 3p sublevel. And then you would have D. I'm not going to get into drawing D, but you can kind of see how each sublevel gets a little bit further away from the nucleus. And so they have a larger radius, higher energy as it builds up to make an entire atom. Okay, so here's an example. Draw the orbitals that can exist in the second energy level. Second energy level can have 8 total electrons. So you will have an S, so 2s, where n is 2. And then you will also have the 2p. So I will have 2p, but I will have 3 of those in different orientations. That one looks really weird, like this. 2p, 2p. So you have 4 orbitals, because there's 8 electrons, and one of those is s, and 3 of them are p. 2 sublevels, 4 orbitals. Okay, so our linking question here kind of links forward. What is the relationship between energy sublevels and the block nature of the periodic table? We will get into this in a later section, but in case you are going in a different order, let's go ahead and look at those blocks. So the periodic table can effectively be chunked into different blocks. The first 2 groups is what we call the S block. Other than helium, which is really part of the S block, we have the rest of those representative elements are the P block. The center section here is the D block, and the lanthanide and actinide series makes up the F block. And we call them that because the outermost electron of the particular atom is going to be in that orbital. So like lithium here, its valence electron is in the 2s orbital, whereas carbon here, its valence electrons are in the 2p orbital, or 2p sublevel. So that's why carbon's in the p block, because its valence electrons are in the p sublevel. And that's true for just about any of them. It's also going to give us clues into how the order of energy increases along the periodic table, starting at 1s and working its way up to 2s, 2p, 3s, 3p, and it tells us like the order of lowest energy to highest energy on the periodic table.